thank you for the introduction. And it was slightly better when I could see you, because like I might have some questions in the audience, but we'll see. Anyway, today I want to talk about distributed systems, because I was always, interested in the full stack when it comes to development or like software engineering. And like, even though I spent so much time on the front-end engineering part, I kind of try to always challenge myself with different things, and distributed systems are one of the most interesting spaces, I think. So today I want to talk about something I am very excited about, which is, I would say, a new paradigm, and shifting gears towards like less work for us developers, and while achieving the same as we do now. So something about me, as I said, I'm a software engineer, currently on sabbatical. It's been 2 months. It's very great. So far so good, not looking forward. And I love tech and innovation. Going snowboarding tomorrow to Austria, so I can't get too wasted with you guys tonight. We'll see how that goes. Anyway, I'll throw this at you right now at the beginning, so you can take a look. This is the CNCF landscape, which is Cloud Native Computing Foundation. And the reason I'm showing you this is that if you try to build distributed systems today, you're probably going to use Kubernetes, right? And this is something that exploded while, when we actually got into Kubernetes and people started creating things. So there's like things like databases, streaming messaging, service meshes, API gateways, there's a ton of stuff. And if you're building a distributed system, you probably should have like at least a small idea what these things are for, because all of these things are trying to solve an issue or like fix a problem that they can help you with. And so they're not useless, they're very useful. Although if you look at this landscape, you might be thinking, are we going the right direction? I don't know. It's getting way out of hand. Anyway, this is the agenda that I came up with. We will look at 5 things, or like 4, because there's too many. And I've chosen these 4, and hopefully at the end of the talk it will make sense why I chose these 4. So just to drive home the idea that I'm trying to talk about. And so we will talk about boilerplate code with an example and what it is, and why do we want to get rid of it. We'll look at how we ship applications today, or tomorrow, or yesterday. We will talk about capability providers and what they are. And then I'll quickly talk about networking, and if demo gods permit, I might have a demo at the end. We'll see. So what is boilerplate code? Can anyone tell me? Does anyone know what is boilerplate code?
Code which repeats, and it's in every project, but you can't rid of it.
Yeah, that's the correct answer. Anyone? Any else?
The boring and predictable code.
The boring and predictable. Okay, yeah, sure. I've got a couple of definitions here. Well, this is from Wikipedia, obviously. They are always right. So in computer programming, boilerplate code, or simply boilerplate, are sections of code that are repeated in multiple places with little to no variation. Then it says something about languages, but it doesn't matter. The better language is, the less boilerplate code, that's what it says, but not important. Sometimes it can be referred to as a functional and non-functional requirements. You can think of it as I have the first section says like that's the code for when you try to solve a problem with your application. That's like your functional business logic, right? And then all the rest, like which HTTP server are we going to use? That's the non-functional requirement. You can think of it also as if you like functional programming. There's this thing called pure functions and impure functions. We always try to push the side effects to the edge of our application, and we do it for a good thing, right? And you can think of this as we know what to do, what we need to do. That's the what of that's the functional requirement, But how we do it is the side effect. So one without the other is actually a useless application, right? Because like you need both. The problem is we've gone like long distances about this. We created things like anti-corruption layers, which is basically, I'll get to this. But other times, it can be referred to as an accidental complexity in one of my favorite papers about, software engineering. This is what I meant by saying whatever I said. This is another perspective at the problem or thing that we're trying to solve. So accidental complexity refers to the challenges the developers unintentionally make for themselves. Like for example, if we are building distributed system, we now have to solve a problem that we didn't have, which is how those computers are going to talk to each other, right? That's a problem that we didn't have before that. So that's the accidental complexity. Essential complexity is obviously, hey, I need my users to have notifications. Anyway, as I said, we went quite long distances. We created things like onion architecture or hexagonal architecture, whatever you call it. It's basically architecture of how we structure our programs so that we can keep our domain business logic pure and then just wrap it in a like a side effect for computation, split in different things. And this is where the anti-corruption layers live, which is basically those adapters or facades that you write on top of some integration library that, like, for example, it's pretty routine that a developer is going to write an application that talks to Redis and Postgres, right? But you in your business logic, you don't treat them like Redis or Postgres. You say like, okay, this is a key value storage, this is a database. So you create abstractions. These are those are the facades and adapters, and you're intentionally doing this because you have, what if you need to change it for something else or whatever. Although I haven't seen anyone doing that, it's useful, right? No, seriously, that wasn't. I'm serious. It's useful. The issue is that when we ship this application, we also ship the libraries and binaries with it, with all those side effects. We're shipping business logic with the side effects together. But I'll get to this later. There's things that can help with this. One of them is Dapper, which is basically, if we talk about Kubernetes, I don't know if you can see it back there, but this is like your pod, or like, well, that's a pod, and that's running your microservice there. And you have a sidecar for does anyone know, who knows what a sidecar is? Okay, 3, 4, 5 people, 6, okay. Sidecar is basically like if you have a Kubernetes cluster, there's like multiple pods running in there, right? They need to communicate with each other. And they're split into pods, and the pods have containers with them. And if you put a sidecar that lives on the pod, then whatever talks to outside or inside to those pods in those containers in there, they need to go through that sidecar. So the sidecar can do interesting things, like for example, you can change the headers of the request, or things like that. So Dapper is basically giving you. I should have shown a code here, but I haven't found any reasonable one, and I have no experience with this technology because I'm not interested in it. But whatever, it's mainly used for like .NET projects, C#. It comes from the Microsoft laboratory. Anyway, let's talk about an example, a concrete example. Yeah. So this is Karen, and she wants to build an app. And in particular, she wants like a dating app, right? And she wants it to be stable and fast, so she builds it in Rust. But that's completely irrelevant, right? It's completely irrelevant because like you can have a Golang project, or like eventually there will be Java, everything compiling down to WebAssembly. So it's irrelevant. It's just like in the previous in the previous talk, there was a question about compile time of Rust. So that's the second line here that I just added a few minutes ago. Because like with languages, it doesn't really matter what you use. Like we always say, use the right tool for the job. But I've been coding in Rust for last couple of years, and I love it so much that I don't want to do anything else now. Because like you have the very decent type safety. What Rust can do, for example, if we want to compare it to Go, Rust can actually make sure that your concurrency is safe. At build time, so you don't even ship runtime errors around concurrency issues and whatever. Also, you get to choose what your runtime is, which is something that you don't get to choose with languages like Golang or Kotlin, Java, because those choices are already made there for you. You don't have any way to change it. Anyway. Rust learning curve is it's probably the one thing that people complain about, but it's true. It's true. What can I say? It's more about once you start. What I always say is that if you are building a project in Rust, it goes like this. Even if you know what you are doing, and then eventually. Oh, I mean, it's not like this deep, but what you are doing in Rust, because of the type system and traits, you are actually you are adding ergonomy to the language, but around your business domain, which means like you can expand things, like iterators for your business domain functions. For example, if you're doing a stock exchange or whatever, you're doing some math around numbers, you can just expand everything that includes numbers for like calculate the mean, just dot mean. So you are building ergonomy around your system, and you get faster and faster actually. So at the beginning, yes, you have to pay, but then it'll get faster. That's what I believe in. Anyway, back to the example. Karen needs to set up a web server, right? So this is the first thing that she's going to start with. I think. I will start with the web server, right? I'm going to have something running. And this is the accidental complexity, right? This is the non-functional requirement. But we have to do it, otherwise it's useless. And what if so we're using some library here. It's actually ActixWeb, but what if in the future, what if there's a bug or like a security hole in this package, or like Prague, right? So this is like a web server, and now someone finds there is a security hole that whatever 0 day hackers can get to you immediately, right? Whatever. Now you have to recompile the application, update the package, and push it again. And the whole package. By the whole package, I mean with your application business logic. Everything has to be redeployed in this microservice, even if it's probably not a microservice. You get the point, right? You have to ship business logic with everything, even though you need to fix a security hole in your HTTP server. Anyway, then she goes and can write some first business logic, which is index PHP. No. But index, sign in, sign up runs, right? Then she figures, I might need to send notifications to users, so she'll go and create her own mail server. Can do it, why not, right? But again, accidental logic. Now she can actually use that. I forgot to mention there is not going to be that much Rust code in this talk, even though it's supposed to be about Rust code. But we are looking at things from, I would say, 10,000 feet, like an overview. So, but here's some Rust code, for example. This is like the ActixWeb. You get injected a service context where you can, which is something you can define on your own. And I have like a mailer there, and I can send email, right, easily. This is actually a business logic, but I don't actually care about what mailer that is, right? It just needs to fulfill some. Interface, right? Like it's an implementation of an interface. I don't care. This is why we abstract those things using those facades, adapters, and anti-corruption layers, and so on. So this is like a quick summary of what I've just gone through. In the pink, you can see that that's the accidental complexity, and that's boilerplate. We can call it boilerplate, and then there's the business logic. So you may be thinking, well, no, I don't care. That's not that bad, isn't it? Is it? I don't know. But there's more. The list goes on. And this is like functional requirements that we need for our dating app, right? Like we need to create profiles. We need to create details of other profiles. We need to like or dislike the other profiles. And real-time messaging. And validate all requests. And so on and so on. But next to it, those are all the things that we have to do, if we are building this app. There's loads if you look at it. Like for example, emit logs to std out. You would be thinking, well, that's nothing. You can just like console log. Well, no. If you want to do logging properly, you should probably use like a tracing library if you are doing distributed systems or whatever. I don't want to go into too much details here. So, which gets me to how we ship the applications today to the cloud or in the cloud. Any questions so far? No? So back then, we used to ship whole virtual machine images. I remember this. I was doing it once or twice. Luckily, it's super strange. I'm hearing myself. Should I cut the microphone on my end? Maybe. You don't need it, right? Cool. Right, back to the slides. So we were shipping whole, virtual machine images, which is like if you look at the computer when it's running. This is somewhere in the cloud. I'm missing a cloud illustration here, but you can imagine. So there's like a machine, and that's running 3 virtual machines in it. And what we are shipping is the image that the machine needs to spin up. And this takes minutes, and this really takes minutes. Not too many minutes, but it takes minutes, right? And also it's huge. It's a huge file that we're shipping. But nowadays, since we got Docker, we are shipping containers. And containers spin up in seconds, like 6 seconds, and it's up. Pretty good, right? Like Kubernetes actually has the health check set to 6 seconds. The first health check. So this actually introduces an error, or like a bug, where we are trying to ship WASM to Kubernetes, because WASM spins so fast that in 6 seconds that's too long, It's like whatever. Nowadays we're shipping images or like containers. They're smaller, but they're still large, gigabytes still, but they spin up in seconds, so it's a lot better, like 60 times improvement, isn't it? Tomorrow, or today, we'll be shipping WASM modules. So you can see, like, there's no kernel. Although Docker can run today, they can run almost. We'll get to it. But WASM apps spin up in milliseconds, right? These are these WASM modules that we can compile to. Even like we can use Rust or we can use Golang, whatever. Java is working on a garbage, like the whole WASM ecosystem and the people around it are hardly working on like garbage collection. So languages with garbage collection can jump in as well. But anyway, today's talk is what we're gonna do tomorrow or in a week. Actually, one thing. So what you're looking at on the right, there are already platforms being built for this model, and one of them is Fermio. You can use their tool called Spin, You just type spin, and it's gonna be like spin new project. It's gonna spin you a new project in Rust, or I think they have like TinyGo in there as well, because TinyGo compiles to WASM already. And then you can do like spin publish, and it's gonna spin it up on this platform, and it's pretty cool. It's like the 2022 Heroku style. Anyway, in a week, I say in a week, but we'll do it now. We'll be shipping actors, and for those who are familiar with like Elixir or Align, this is a very common model there, where you have like an actor that only includes your business logic and seeks other services for fulfilling those side effects, right? They don't have an abstraction that we are going to look at, but it's pretty cool. So wasmCloud, as you can see the logo up there, has actually implemented this, and what it does, you can see this on the machine. Like you can have like a wasmCloud host, which is a runtime written in Elixir actually, and it runs those WASM modules and capability providers next to it, and you can connect them together. Basically, you just wire it like you wire, whatever, electricity, and it just works. We'll have a look. This is their website. It's what I'm going to talk about. But then also it's an open source, so you can take a look at the code, how it works, everything. And then there's a somewhere.
Isn't wasmCloud written in Rest?
So the runtime. So there's multiple pieces, right? But the runtime is written in Elixir, and the capability providers that you're going to look at written in Rust, Go, whatever what have you. Can be whatever. I mean, whatever that compiles to WASM, right? Which is not Java still. Anyway, pun intended. So I just show you wasmCloud. That's the open source ecosystem, I would say. And there is already a platform by the same guys called Cosmonic. That's the real deal. That's like the new Heroku style. Like you just write your actor, connect it like this. They even have this nice UI where you can drag it in your mouse. Super cool. I really recommend. They are in alpha testing, so you can get on the waiting list. That's super cool. Which gets me to capability providers and what they are, right? So we know that we have these functional requirements, non-functional requirements. They have to be there, both. But we have to have like a line between them, right? To distinguish. We do, even in our systems today, we design by contract, which is something you could think, I guess I'll skip this. Yeah, I'll skip this. Anyway. So we talk about actors, and we have a capability provider. So between them, we have to have some linking or like connection or networking, and this is done by either if you are building today like a distributed system today, which is probably most of your startups, they use Kafka, for example, right, for these things like how to talk to service kind of thing. Yeah, that gets me to networking. We already spoke about this distributed systems. I'm sorry about the slides, they're somewhat mismatched to what I'm saying. But this is what I found on Wikipedia. Like basically distributed systems is a bunch of computers that need to talk to each other. Done. And we can do it. How do we then like talk to other computers, right? How do we know the computer's IP address? How do we handle fault tolerance if our request didn't work out? This is what we build. This is why we build things like service meshes, which basically are those sidecars that I mentioned. And you can say, I need to talk to database, and it's gonna find you the right IP address, and so on. It's going to make a request, and if it fails, it's going to retry the request for you. Yeah. So basically, we're building abstractions for ourselves, so we don't have to write this retriable code in our business logic, right? That's why. The other thing is the event mesh, which I just briefly spoke about. That's the Kafka thing, where you have like a central or like even distributed Kafka cluster where services send message to, and it's going to publish those messages to other services and so on. But this is how we build systems today. If you want a high, reliable system that's fast and distributed. wasmCloud, on the other hand, is taking this a step further, where it only spins those WASM modules. And what's interesting about WASM modules is that you have to give it. They are secure by default because they can't do anything, on their own. You have to tell them how to get to file system or how to make a network request. You do this through something called WASI, which is the new WebAssembly system interface. We're not going to talk about that. Maybe over a year. I'm happy. But what wasmCloud does is that it uses this technology called NATS. And NATS you can think of as Kafka on steroids, I call it. It's basically a thing to build platforms. It's like it's like a sidecar, but it can be handled by, well, it provides this. It's like Kafka, but it's. I'm getting lost. Whatever. I need to hear. So wasmCloud. We talk about service meshes and event meshes. So those are like network. You could think of it like a virtual private cloud. Where those computers can talk to each other, and they call it Lattice, which is like a service mesh, but in fact it's like technically it's an event mesh. It's the NATS that it's more close to Kafka, but it can deliver the functionality of the service mesh. So that's why I'm saying it's Kafka on steroids. It's very interesting tech, and it's also lightweight. It's written in Golang, and it's like one binary, like 3 megabytes, and you can use it to connect things around the world, like in different clusters, seamlessly. Secure by default. So this is what wasmCloud uses under the hood. And this is how it sort of looks like. So you have like wasmCloud runtime in Cloud VM, could be AWS, whatever. And then you have like a local computer. And you have like your actors. Then you have your capability providers. Those are the red things. And then you have a NATS gateway. You could call it, they call it leaf node. NATS leaf node, and that's connected to, for example, there is this thing called NGS by the authors of NATS, which allow you to connect seamlessly, edge to edge, from different worlds. And NATS is intelligent enough that if you have, for example, if here was an HTTP server, NATS is intelligent enough that if this actor needs a HTTP server, it's going to go to this one, right? It's not going to go to over the world to the far one. So that's really cool. They call it flattened topology, obviously. Here's how NATS is used in wasmCloud, but I guess that doesn't make sense yet. It'll make sense, I promise. Now we can look at the demo, which hopefully is going to work. So here I have a thing that I could just generate from scratch. Should I do it? I have time. So so you can use like wash. Wait, let me make it larger. Sure. Is that what you wanted to say? So I'm in my workspace. I'm going to do wash new actor. What are we gonna call it? Well, we're gonna use an empty actor. Echo time go. No, we're gonna do it in Rust. What's the project name? PragueJS. Right?
What a name.
What a name. Let me open the project. Like so. And what does it generate? Okay, let's take a look. So there are a bunch of things. This is like Rust. There's even a CI configuration for GitHub, whatever. But there is one file, right? And what does it say? So this is like what would you call it? Hello world, right? Example. It's just a Rust code, and it has 24 lines of code. And what it does, it receives a request, HTTP request. That's it, and it parses the request, as we can see here, and takes the name out of the query parameters, and if there's none, it puts world. So this should give us hello world if we don't provide query parameter with name, right? Everyone sees this? And what's nice about this is that we didn't have to choose or do anything else. Like, what is this? What is the HTTP server going to look like? What implementation are we going to use? So we can build this by running make. It's going to take a while because like those compilation times, right? I mean, they're worth it because if you can catch the bug before I ship it to users, I'm happy. Done. So this generated a wasmCloud module with capabilities, wasmCloud HTTP server. Let's take a look at how we can use it. So what we can do, we need to run that runtime, right? We need to spin up that runtime that's going to take care of our system. There has to be, like, you know what Kubernetes does, right? It's just like a small operating system that makes sure that everything is up, always up, right? If something goes down, it's going to bring it up. This is what this is. That's what wasm wash up does. It's going to spin up that host runtime. It should give us even this UI running on port 4000. And we can see on the left we have actors. On the lower right we have hosts. We can have multiple hosts connected together. We saw that, but I'm not going to demo that today because I would have to spin up like a AWS cluster, whatever. And we have providers. So what do we want to do? We can upload our actor, which was, what was it? PragueJS. Build. This is the module. Can everyone see it? All good? Oops. Let me make that tiny bigger, like this. So we have actor, but it's not doing anything, right? Because it needs that HTTP server. So what we can do, we can even try downloading that HTTP server from the internet because it fulfills the interface, right? This is like a repository of like basically the same thing that you're used to from Docker, right? You can just say from where, which version, submit, and hopefully, if there's internet, I should download the thing. Like there's still, work to be done on this UI, but as you can see, nothing's happening. Let me check the logs. Still nothing. I'm just gonna, I made sure the demo is gonna work. I mean, I'm still not sure it's gonna work, but I cloned the repository of capability providers, which I have. Oh wait, there it is. It was just slow, right? So now we have a HTTP server capability provider. Now we have to connect them together. This is the parametric linking I was talking about. We have to somehow tell them, you talk to this guy, or like you talk to this capability provider. So we say, this PragueJS actor talks to HTTP server, and it's this contract that you're gonna use. We submit, we look at the logs, and it should tell us, there it is. It's running on port 8000. So let's take a look at 8000. And we see hello world. And and I can put like hello world. Do you like this?
I've never seen more complex hello world.
Yes. Well, you want to see something cool? I'll show you something cool. So I'm gonna kill this actor, right? And I'm gonna spin up a different actor that I wrote. It's slightly more complex. I'll show you the code. Not PragueJS. It's this one. So this guy is just like the first one. You know, implements a HTTP server, but also needs things like blob store, like it needs to work with files, right? So what this does, it receives the same request that we just talked about, like, you know, query world, it can have a name in it, but what's it gonna do? It's gonna put it in a file. So it's gonna make the file with the name that we provide, and also put the same content into it. Like, very stupid, right? Very stupid example. But let me spin it up, because I'll show you something cool. Workspace. This is called wasmCloud store. And I'm not sure it's going to be... No, it's not connected. We need to define the new link. So we give it HTTP server. Oh, wait. Sure. Why is it still there? Come on. As I said, it needs love. Anyway, so I connected the actor with our HTTP server. Now I need to add new capability provider, which handles the file system, right? So I need to give it like, hey, this is the capability provider that's going to handle a file system for you. I have it compiled somewhere here. It should work. Come on. Did I kill? I did kill it, right? Oh boy. Where is my wash up running? Well, I'll do it again. Right, let me try. Second time, add this blob store. Right, that's there. I'm gonna tell it to download the HTTP server from the registry, as we did before. It's on. Now we're gonna add the actor, which is this new thing. Wait. And now we need to connect them together. We're gonna use this as HTTP server now. And you're gonna use this for the blob store contract, yeah? So now if I visit this URL again, it's now saving it into a file that's printed out here. So let's take a look. What's in that file? TMP, where was it? NVI there. See, the contents is Roman. But what if we do Philip? You should have a Philip in there, right? Now there is a file that has the contents in it. Like, this is not the cool part. The cool part starts now. So look, what I can do, I can actually start a new provider that's gonna. It's basically another blob store provider of the same contract, but it's gonna use the S3 bucket of AWS, right? And what I can do is that I can hot swap it. Like, I'm just gonna change the parametric linking between them. I'm gonna use the AWS capability provider, blob store, and I need to give it a configuration there that has the you know, if you work with S3 bucket, you need these access ID and secret tokens and so on. That's what the file contains. So I just need to tell it where it is. I could also provide it here as like an access token, but this is just simpler for now. But if I do it, let's give it a try. I'm gonna refresh, and then I'm gonna go to AWS, right?
There is no proof the bucket was empty before.
We can try another name. We can try another name. Give me a name. So there's S3 bucket here. There should be a PragueJS bucket. Let's see if it works actually. There it is. You want to try another name? Sure. What do you say? Give me a name.
Peter.
Peter. Done. Let's check the bucket. There it is. See how I hot swap the capability provider and it still works. And that's the end of the demo. Hope you like it. I'm super excited about this stuff. As you can see. Anyway, that's the end of the demo. This is what we just did. We have an actor, we have like HTTP server, you can see those lines where they point, that's the direction of dependency. So HTTP server depends on some actor, right? We depend on blob store, and then we hot swap to the other one. This is like so huge that even the co-founder of Docker says that like if we had this in 2008, we wouldn't have to make Docker. Done, you know? I mean, this is not going to replace Docker, but still. They are now catching up with, it's how I call it, obviously they didn't work. But what this is that they support, you know, you would be able to ship these wasmCloud modules to the registry, to the Docker registry. Currently it's only supported by Azure. This is like what we talk about, what we could talk about over a beer, if you want. That's on the right. There's very interesting stuff happening in all those things. For example, I didn't show you how those contracts are generated between actor and capability providers because they are now obsolete actually because of WebAssembly components and PIT, something called PIT, which is like WebAssembly interface, special type of, well, it's a new type of like file format, but you know it's language agnostic, so you can generate code from there for your Rust or Golang stuff. Anyway, thank you very much. I hope you like it, and that's it.